So this first part is going to be on what is called function composition. Okay? Sure. So function composition, this is the one I'm going to do by hand quite a bit, all right? Let's do like a little tiny example of this, all right? Let's say that we have a balloon, all right, like a party balloon. You know, maybe getting ready for the Super Bowl or something, I don't know, all right? Got little party balloons going on. And so air in the balloons, obviously the volume. And it will make it spherical just to keep it simple. So that's going to be 4 pi r cubed divided by 3. That's the formula for it. You can look it up if you don't believe me, but that's what it is. All right. And we have a pump because we're going to have a whole bunch of these balloons. I'm just going to keep blowing them up. We don't want to do it by manually, so we'll have a little pump. And what the pump does is the pump fills the balloon so that the radius expands (1.5 centimeters). We're going to do centimeters because it seemed like that made a little bit more sense in a per second thing. Okay, I thought 1.5 inches per second was quite a bit, so I said we'll just do 1.5 centimeters per second. So what we have here is we have a volume of a balloon, okay, which would be VR. That's a function. We can write it as a function, r cubed divided by 3. And then we have this radius, which is increasing, say, we'll call it r of t, which is increasing by 1.5 centimeters per second. Does all that kind of make sense so far? Okay. Okay. So, this is an r here. I didn't write it out very well. So, what we want to do is write a function for the volume in terms of t, which is the time in seconds. All right? So right now, our volume is written in terms of r, 4 pi r cubed, all right, divided by 3. But we want to write in terms of t, so we can kind of get an idea of, you know, how long is it going to take for me to get to a certain amount of volume, right? Maybe I kind of know what it's going to be, so I don't want to break all these balloons. So I know if I get to a certain amount of volume, I know to stop it. All right, so something like this. So we want to come up with v of t. What is that going to look like? All right, well, we know this. We only have one variable here, and that's r. So we know we're going to have 4 pi, and we know we're going to have a 3. But what would we put in that r spot to get it so it's in terms of t?
1.5.
Yeah. And of course, we'd have to cube that, right? Well, you just did function composition, because that's what it is. So function composition is basically taking one function and substituting it in to the other one. So then you're composing them together. Right? That's what function composition is. So what we did was we took this one here, okay, and put it in there. Since this is r and this is r, we put it in there and thus came up with this function composition. That's what it is. Okay? So function composition is basically just replacing function composition is substituting, I think is the best way to think of it, substituting one function into another one. Now, the book uses this kind of notation for that. F-O-G, looks like fog, doesn't it? Okay? But it means this. So I like to use this notation because I think it intuitively makes more sense than this does, but unfortunately the book uses the fog thing. Okay? Whereas in this case, you would take the g function and put it into the f, because that's kind of the way it's written. F of g of x. So the g is going to go into f. Whereas this one's f-o-g and then an x. So I'm not exactly sure what's going on there. It kind of looks like it might be multiplication, but it's not, because this is an open circle, which means that it's composition. All right? So that's kind of the way they like to do it. Remember, they did the additions and multiplication stuff that way too, and it confused some of us. And then on the test, I wrote it in my notation, and everybody pretty much got it right. So it's crazy how just a little bit of notation will make a difference. So let's do a little example here, and then we're going to talk about domains and ranges and stuff. Okay, we're going to start out pretty straightforward. So what we're going to do is go ahead and do this f of g of x here. All right, but we want to kind of think of it like this, because that intuitively makes more sense. So the g function right here is going to go right there where the x is into the f function. All right, so you always start inside out and work your way out. Okay, start on the inside and work your way out. So what's that going to look like? Well, pretty simple. So we're just going to take this g, and I'm going to put it where that x is, so it's going to look like this. And then I'm just going to kind of distribute and do a little bit of algebra here, and there it is. And that's it. And that's basically all you're doing, is you're just taking and substituting one function into another. All right? That's really all there is to it. Well, let's do some more. Okay, so we'll do here, we'll go f of gx, which again is this. And we'll also do it the other way, which would be this in this case. Okay, so we're going to do it both ways. All right, so this one, we're starting with the g. So this function here is going to go right where that x is. Wherever the x is, that's where I'm going to put it. All right, and then I'm going to do whatever the rule is. So here, all right, we're going to get 1 over 3x minus 2, and that's it. Because that's all there is to it. Right? G into the f. That's it. That's done. We'll run this side. Now we're going to go the other way. So we're going to put the f function into there. Okay? So there's a difference. So here we go. So let's try this out. So now we're going to get 3 parentheses, put the f function in there. And then do some algebra to get the answer. Okay? Are they the same thing? No, they're not. All right. Now, let's go back in time a little bit here. 3 times 2 equals 2 times 3. Right? Do you remember what that's called? What property that is? It's got a name. If you don't, that's okay. Huh? Commutative. Yeah, it's commutative property. Says it doesn't matter which order you do things in, it's going to be the same. All right? Function composition, we just showed, is not commutative. All right? So just because you do f of g of x and you get an answer, that doesn't necessarily mean g of f of x is going to be the same thing. All right? So it's not commutative. All right? I saw one here I wanted to look at. Oh, okay. No, don't do that. All right, so let's try this one. So we're going to go h of f of x here. So which function is going to go into which? F's going to go into h. All right, so wherever I see an x up here in this h, that's where this is going to go. See, now it has to go in 2 spots. So I have to put it in both spots. So here we go. So we're going to go 3x minus 1 squared plus 2 times 3x minus 1 plus 4. And so we're putting it in both spots. So then we just got to go ahead and do some algebra and kind of clean it up a little bit because it's not real clean right now. So we're going to clean this up. So I'm going to FOIL that. So I'm going to write it twice. That's what I like to say. Write it twice. 9x squared minus 3x plus 1. And then we'll distribute that. Oh, the 6x's are going to go away. I sure didn't plan that. 3. Negative 1 plus 4, yep, 3. All right. So that's it. Wherever you see an x, you got to put in the f of x. Whatever you're substituting inside. Okay. Any questions so far? No. All right. Here's what we're going to do. We're going to do this. Okay. Let's consider this little f function here. Okay. And I don't know what it is. I'm just going to make up some stuff. Okay, let's say it looks like that. All right. Now I'm going to divide this with a different color here. Try to make a point. Here's a g function here. Okay, this is a pretty important idea. All right, we're going to go g of Yeah, f of x. All right. So when we're doing this, so here's our inputs for f, and here's my outputs. Right? There's my outputs. In function composition, what happens is that our outputs become our inputs for the next function. So these numbers here become these numbers here. They become the inputs. All right? This is an important idea because when we start talking about domain and ranges, we want to make sure we understand this part. So this here, the outputs become the inputs here. Now, I don't know what the g function, again, I'm just going to make some stuff up. I have no idea what this thing looks like. All right? But the important idea is right in this part here. Okay? Now, the whole thing then, if we looked at this composition, it would look like this. 1, 2, 3, 4, 5, 20, 22, 24, 26, and 28. So the final answer is right here. Okay? So that's what's happening with function composition. So you start out with this, right? Okay, gives us these outputs, and then these outputs become the inputs into this function here, which gives us a new set of outputs, and then these two things together make up the function composition. Okay? That's how it works. Now, why is that kind of important? Well, let's take a look at something like this. Okay? So let's say that we have an f and it is 2x plus 3. Okay? And let's say we have a g that is the square root of x. Straightforward square root of x. All right? And let's write some domains down and some ranges. Now the first one, if we graphed it, what would the graph be? A line. What's the domain of a line? All reals. Doesn't matter. You pick a line, unless they're horizontal or vertical, the domain's all reals. All right? What's the range going to be? Okay. So, we're going to do function composition. All right? G of f. So, we're going to take, this is my output now. Right? It becomes the input over here. Does that work? No. Why not? What's going on over here? X can't be what? Square root of 0 is okay. What can't x be? Can't be a negative, right? Okay, so right now, some of these aren't going to work. Okay? So that means that we have to restrict that domain. So those outputs that I'm getting from the f function, they're not all going to work. All right? So I got to restrict it. Okay, so that I get the numbers that are going to work. And that would be okay. What is the range of this thing here if it's a square root? We got to think about that. Let's see what that graph look like. What would be the range? It's got to be greater than or equal to 0. Yep. Okay. So that means if I compose this together, right, my domain would be all real, and my range is going to be y is greater than or equal to 0. That's the composition. So we're taking the f function, right, and we're substituting it into the g. All right, so this would be g of f of x. So when you're doing these, you kind of got to be careful of that idea. All right, because you might have to do some restrictions on some domains. Okay, let's try it the other way around. Same ones, let's not just, but let's go with this. Let's go f of g, all right? So now, the g function here, the domain and the range. All right, here we go. So the domain of the g function is going to be what? It's that square root that I had over here. What's the domain? Greater than or equal to 0. Okay, so that's the domain, right? It's going to give me a range. What's the range of the g function? Okay, now, then that becomes, right, this becomes the domain for the f. So that goes over there. But what's the domain of the f function that we had up here? Yeah. So is it still all reals? No. Because remember that these outputs now become these inputs. So these are the only ones that are going to get input into there. All right. All the rest of them aren't, because that you can't have any negatives. So then this is going to be x is greater than or equal to 0. All right. So that kind of changes things a little bit. And then the range, well, the range is usually all real numbers, but I wonder what we would get if we just had x is greater than or equal to 0 into that f function. What would the range be then? Greater than or equal to what? Not 0, but you got the right idea. Now remember, you're putting all these in there, right? Putting them into this up here, this guy up here. I can barely highlight it right there. So, yeah, what are we going to get? Greater than or equal to 3, right? Because if we put 0 into there, okay, we're going to get 2 times 0 is 0 plus 3. So that's going to be smallest 1. All right? So it changes the game a little bit when you start having to restrict domains.
So it becomes the y-intercept?
Well, becomes bigger than it, because you don't, normally on the 2x plus 3, right, that's a line, right? So it's just a line, 2x plus 3, so it looks something like that, right? But we're restricting the inputs that we're going to put into that, so that really it's just starting right there. Okay? And that's because we can't have any negatives coming out of that square root. Right? Okay? So it's a little different. So you kind of have to be careful with some of that when you're doing some of these problems. Because it says, I'm looking at some now, it says state the domain of each composition. All right? So you kind of have to be careful of it. Here, we'll do another one here. They do some square roots, so what the heck. All right, so let's take a look at these. Okay, so let's do g of f of, oops, x. Okay. All right, so I got to be concerned about the domain and range of that guy right there. I got to watch out, because I don't know what's going to happen there. So let's talk about that. So let's see. We'll put it over here, I guess. So what's the domain of that f function? What numbers can we not have?
0.
Can't be -1, right? Everything else is okay, but we can't have a -1 there. we have a negative 1, then we're going to have a problem down here on the bottom because that's going to give me 0. We can't have that. All right. The range. I don't know. I might have to graph that. See, I'm not sure. When am I going to get there? X over x plus 1. So let's go ahead and graph it, and let's see what it looks like. Or I'll let you kind of graph it, because if I graph it, then I'm going to have to switch back and forth. And so you kind of graph it and see what the range is. Let me know when you get it. Did you find anything out yet?
Equal 1 or negative 1?
Doesn't work at negative 1?
It does.
Yeah? Just 1. Just 1. Okay. So, remember, this becomes my new domain for what I'm going to have here. Let's still talk about the domain of this, right? Domain range. Okay, here we go. What about the domain of the G? What is that going to look like? What can't we have there? X. Can't be negative 3. Can it be negative 2? Yeah. Can it be negative 2.5?
Yep. So greater than negative 3.
It can be negative 2.5?
Well, it can be.
Wouldn't we get?
It can't be greater than 2.
Okay, so it's got to be greater than or equal to negative 2 then, correct? Does that make sense? Negative 1's okay? Right? Okay? All right. So, but what about now if we put this composition, right? This is going to slide in there. Okay? So this says x is greater than negative 2. Is that going to be okay? Do we need to restrict anything there? Yeah, what do we got to say besides that? X cannot equal 1. Okay? So we got to say that, yeah, this is okay, but x can't equal 1. All right? Okay? So we're okay with all the rest of the numbers, but can't have 1. So that means that our range might change a little bit, right? Because now we can't put 1 in there, which means that we're not going to get a certain number for an output. Okay? We're not going to get the square root of 3 is not going to be part of that range. Everything else is okay, but the square root of 3 is not going to be part of that. Okay? So y is greater than or equal to 0, but y is never going to be equal to the square root of 3. All right? Because we can't have 1. Okay? So that is for the composition. So it's kind of goofy stuff. All right? You kind of got to be aware of it. So let's just graph a couple of them for the heck of it and see what happens. All right, so if I go here and go into Desmos and let's graph some. And let's get a visual for kind of what's going on. So what was that? That first one we did, okay, was right there, f of x. So I'm going to go like this. So I'm going to go f of x equals 2x plus 3. So this is the one we did a few minutes ago. All right, then I'm going to go g of x equals, here let me put it on projector mode so you guys can see better. Square root of x. All right, now watch this. So I'm going to go g of f of x. And by golly, it graphs it for me. Okay, so here's the red one. That's the line. Okay, there's the red line. All right, here's the blue. That's the square root. And then here's the composition of that. So this is going to go right inside of here. Is that how, do I have it right? So I took this one and put it inside of there. Notice that we said for that the domain, we had to restrict it. So x was greater than or equal to 0. Which is this one right here. Okay. And the range now is greater than or equal to, how come that's, I wonder if it's doing this incorrectly here. Let's try this out. I thought it would do it. Maybe it's not. Oh, it's doing it okay. So you can kind of look at them from that, get the ranges anyway by looking at them from that. Okay. It's a little bit, if we turn these off, there you go. You can get those ones. Let me turn that one off. And if we go the other way around, f of g of x, there it is. See how it's greater or equal to 0 here and 3. That's the one I wanted right there. That's the one that we did. Okay. We said that the domain had to be greater than or equal to 0, which it is, and that the range is greater than or equal to 3, which it is. Okay. That's the one that we did. All right. So Desmos graphs it for us. All right. And it also shows you it's not commutative because the other one was there. And they are different graphs. Okay. And we could do the same thing for the one that I just did, which was this one here. X divided by x plus 1. And this was square root x plus 2. Okay. Get rid of this one, I don't need it. So here is the g of f, or f of g, sorry. Okay. This one, the domain would be greater or equal to -2, and the range has to be greater than or equal to 0. That's what we got. Okay. And then if I went with this one, I get a whole different thing going on there. Okay.
I thought we were doing the G of F. G of F.
I might have had it switched a little bit.
Okay.
Yeah.
Yeah, that's what I was going to say. Wait, it shows -2.
Okay. And then this one looks like that. All right. And it doesn't go and again, that's just a restriction on the domain. Okay. Which is what we're trying to show you. But that's what function composition is. The only really tricky part is the domain and range thing. They ask you for that. Otherwise, you just substitute one into the other, and it works out pretty well. Any questions on any of that there?
So when we did the f of g of x, the g of fx, say we did that one, right? So we would do the function, the domain for that one will be the output of f of x.
So G here,
Yeah.
right? So there's a domain for G, correct? And then you get a range, right? So the range, that becomes the input for the f.
For the f.
Because you're taking, so you're working inside out, right? So you're taking the G function and you're putting it into the f. Okay, so you're taking it out of the G and putting it into the f.
So then the range for that one becomes, of g becomes the input of f.
Input of the composition, right? It becomes the it's the input of the composition, okay? Not just for the f, but it's the f of g. So you're taking the G range and you're putting it into the f to get the composition of it. Does that make sense? Okay. Because the f function, standing by itself, has a whole different domain and range. Remember that one we did with the line and the square root, and it had all real numbers, but the square root didn't, so you had to restrict the domain on it. Okay. But you're only restricting it because it's a composition. All right. So the composition is where the problem comes in, and a lot of times it doesn't make any difference. Why they can't? Well, because, and Desmos isn't going to show you that. I don't think. If we, well, it would be really hard to do it. Because, here, let me show you. So we said that x cannot equal 1, right? Okay. So if I put 1 into here, I'm going to get the square root of 3. So if 1 isn't in the domain, then I can't get the square root of 3 for a range. Okay? But Desmos isn't going to show you that when you graph it because it does pixels to the graph, so it connects pixels, and you won't see it. And the square root of 3 is going to be, you're never going to get to it on there if you play with it enough. You just won't. So it won't show you that. Any more good questions about that composition or anything? Did you want to see more examples of composing some functions? Or are you okay with that? I mean, I'll give you some problems to work on. Yeah.
So Mr. Patterson, on the previous note, I was saying that the output, which is the range of the inside of the brackets, becomes the new input of the function that's outside. Is that correct?
Okay, so let's just I'll make it kind of a simple here, okay? All right. So 1 in here is negative 2, 2 is negative 1, 3 is 0, 4 is 1, right? Okay. So if we put that into this function to find the composition, now we're doing a composition,
yeah,
right? Okay. Then these guys go there.
But is that for g of f or f of g?
So that is going to be that one.
Okay.
So like for example, let's do this. Let's say f of, maybe this will help, f of 2. Here, let me do this. Negative 13, negative 9, negative 5. Let me get this out of the way. 2 in here is 3, right? Yeah, 3 in there is 7. Okay, so here's what I did. So here's x's and y's for the f, right? Here's x's and y's for the g. Okay. So let's pick a number, say f of 2. Okay? So looking at that chart, f of 2 is what number?
-1.
Okay, now that -1 is going to come up here. Right? Now what is -1 equal to? -9. So that means if I do this, right, and I say I'm going to take g of f of 2, I better get -9, right? Okay. All right. So let's do it then. So we're going to take this guy, put it right in there. Good so far? Now, so this is g of f of x, right? Yeah? Okay. Now let's try this out. G of f of 2. So now I'm going to take and I'm going to put 2 into this function here. That's how it works.
Okay, it's just earlier in the problem we did the g of f of x.
I probably had it backwards, maybe. Yeah.
But even when the graph shows that, okay, maybe it wasn't that.
Okay. But that's how it works. Okay.
So the output of the inside becomes the input of the outside function.
The output of the inside becomes the input of the, yeah, I see what you're saying.
Okay.
Yeah. Yeah.
And that, so the range becomes the domain.
Yes.
Okay.
Yes.
Unless there's a restriction.
Of the composition.
Yeah,
right.
the composition.
Okay. And that's why you have to restrict them, because they don't always, those domains, the range of this one might not match the domain of that one. That's why you got to restrict it. Okay. Most of the time, it's not going to be an issue. You're just going to plug away and go. But there are some times where it could be an issue. All right. Especially with square roots.
Yeah.
Square roots and rationals, where you're going to have those restrictions. Okay. Most times, it's not going to be a big deal. But that's a pretty good example there. Okay. Any more good questions? Okay. So let's take a little break. I'm going to go and get that other stuff to hand out to you and put them into the spreadsheet thing here. And then we'll do inverses. Take a look at them. Okay, let's take a look at a function and its inverse. All right. And this is the one where I did some GeoGebra stuff, and I placed some links in the My Courses thing. So let's take a look at those, and then we'll come back and do some more things with functions and inverses on the tablet here. So I'm just going to kind of pause this for occurs when we switch the domain and range. So if I have a function f, all right, and I have a domain 1, 3, or function here, 2, 5, 3, 8, 4, 12. Okay, there's my function right there. The inverse, which is symbolized by that little -1, would be switching these things around. So we're switching those around, okay? That's an inverse. We're switching the domain and the range. And those graphs are reflections over y equals x line. Now we're going to use that idea to find an inverse. There's two ways to find an inverse. I'm going to show you kind of both ways. All right, so we're going to find an inverse. Finding inverses. How do we do that? All right, let's do that. So let's start out with a function f of x equals 3x minus 2. All right, we're going to find the inverse, f inverse of x. That's how you symbolize it. Okay, two ways. One, first thing you do, set it equal to y. First thing, set it equal to y. Now remember, in an inverse, the domain and the range switch. So what we're going to do is switch x and y. Like that. So we're going to switch them. Okay? Now we're going to solve for y. So now I'm going to put over here, solve for y, because that's what we want to do. So add the 2, throw it over here, x plus 2 equals 3y, divide by 3, divide by 3. There's my inverse. So f inverse of x is equal to x plus 2 divided by 3. All right, that's how you find an inverse. So you write, set it equal to y, switch the x's and y's because you're switching domain and range, solve for y. Boom, there it is. All right, let's try another one. Okay, let's try another one here. F of x equals x squared plus 3. All right, so we're going to find the inverse. Okay, find f inverse of x. First thing, set it equal to y. Switch the x's and y's. Because that's what happens in an inverse. Subtract 3 because we're going to solve for y. Got to get rid of y squared. You're going to square root. There's my inverse. Now, some of you might say, hey, when I square rooted, when I was solving these equations, so one other time in my mathematics experience, I put a plus or minus in front of that. How come you didn't do that? Well, we'll talk about that in a little bit with that next thing we'll show you, that next link. You'll see why we don't. All right, but there's my inverse. Okay, there's my inverse. Now, I told you I'd show you two ways. Okay, so that first one we did was 3x minus 2. Okay, first one I did was this. So here's what I want you to think about. Suppose that we knew x was 4. Okay? So I want to find f of 4. Tell me, if you were to do this on your own, by hand, okay, what would you do first? What would be the first thing? And then what operation would you do? So we'd multiply 3 and 4. Okay? Then what would be the second operation you would do? Then you subtract. Okay. Now, an inverse is just the opposite and the reverse of that procedure. Okay? So, we went multiply, subtract. Okay? For an inverse, we're going to reverse it and opposite. So instead of doing multiplication, subtract, we're going to do the subtract first, but we don't want to do the opposite. Or we want to do the opposite of subtract, which is what? Okay, so the first thing I would do is add 2. All right, so whatever I'm going to do, I'm going to add 2, x plus 2. Okay, then multiply by 3, but wait, we want to do the opposite, which is? Was that inverse x plus 2 divided by 3? Is that what it was? Yeah? Yeah. Okay? So what about that other one? Let's see, the other one was x squared plus 3? Okay. So think about it. All right, we're going to find the inverse. So think about, well, gee, if I knew what say I know what x is, say it's 4, again, okay, what would I do first? What's the first thing? Now think about it. If you know what 4 is, you put it into that function, what will you do first? You're going to square first, right? Okay, then after you square, what would you do? Okay, now to find the inverse, okay, we're going to reverse it and opposite. So x, what would I do first? Subtract 3, and then what do I have to do to, what's opposite of a square? Is that my inverse? Yeah. Okay. All right. So, be honest with you, I think the first method is going to work more often and is easier to do for harder inverse functions. But this one's pretty slick, for easy ones. All right? Okay? So, it really kind of depends on what you have. For example, if we have something like this, and we want to find the inverse of this one. Now, this is a little tricky. So I'm going to set it equal to y. And then I'm going to switch the x's and y's. And you're going to look at this and go, how in the heck do I solve for y in a deal like that? That looks pretty tough. Well, here's what you want to do. We're going to set it into a little proportion, do some cross multiplying. Okay? So far, so good? Distribute that. Okay, now remember we're solving for y, so what would be the next step? Do what? Maybe, but that's just going to get us y plus 2. How about if we do this? And then what? Now what? Yeah. So there's my inverse. 1 minus 2x divided by x. Okay. Now that would have been tougher to do the other way. So when they're like this, when you get a rational, you're better to try doing it that way. Okay? It's just hard to do it the other way. It's just, but those easy ones you could. Okay, but the setting it equal to y and switching the x's and y and then solving for y works really well every time. Okay? All right. Let's take a look at that other link here. So I want to come back to this. Go back to this guy here. I want to show you. This is kind of nice. I didn't design this one. So if I go back to here and go to this one and get to the links. This one's inverse part 2, I called it. Okay, so here is a parabola. It's y equals x squared. I think he's got written there, here. Okay, and what we're going to do is take this thing down here, and if you move it along, okay, it just decreases it. But put the reflect on, and now you see, hey, there's the inverse. Okay, but we might notice something about this blue graph and this green graph here. Here's my dotted line that shows the reflection of those. If we focus on the green graph, is that green graph a function? Nope. No, look at that vertical line test. Isn't that slick? Wish I had made this. Okay? That's not. Okay? But as soon as I take this thing and say, okay, I want to restrict the domain so that now, boom, right there, now look at that. Is it a function now? The green graph? Yeah. Okay? So that's why you don't do the plus or minus on the square root, because the inverse turns out to be not a function, and that becomes an issue for us. All right? That's why. Okay. Now, there's something else on here this guy has called a horizontal line test. Okay. Now, the horizontal line test is going to tell you, hey, if I got a function, right, and it crosses a horizontal line 2 places, then what are you going to know about the inverse? So if we have a graph, the blue graph here, it's my original f, okay, and I put a horizontal line through it like this here, okay, and it touches it in 2 spots, then what does that tell you about this inverse? It's not a function. Okay, as soon as I change this blue graph, so all of a sudden, there it is, horizontal line, oh, I'm good there. Notice I'm also good on the green one, okay? Man, that is really slick. Okay? Really slick. I think we'll let you change it for different functions. Let's see. Maybe we can put a 3 up there. I don't know if it'll do it or not. Oh yeah, there it did. There's the green. Okay? Man, that's really neat. Okay? There's the green graph. Is the green graph a function? Yeah, sure is. Check out the horizontal. Look at that. Works. Okay? I know. This guy, that's good. I wish I could take credit for it, but I can't. All right? I don't know. Well, probably can't. I don't know. We're probably limited to what we can put in there. We can put a line in there, but that's not going to be too exciting. All right? But that kind of shows you a little bit about the graph and the reflection. Does a nice job with the reflection there and the horizontal line and the vertical line test. Okay? So, couple things here then. Horizontal line test. So if a horizontal line I'm going to run out of battery soon. If a horizontal line crosses, intersects, touches, whatever word you want to put in there, the graph of a function in two or more, I guess it could be, or more points, then the inverse of the function is not a function. I don't know if I worded that very well, but okay. So if a horizontal line crosses the graph of a function in two or more points, then the inverse of the function is not a function, okay? So, in other words, if we have a parabola like this, horizontal line touches it in two spots, okay, that means that the inverse of this, which looks like this, okay, is also not a function because it doesn't pass the vertical line test, which means we have to restrict so that we only have this part. All right, so then when we do the inverse, then we're okay. All right? That's what the horizontal line test. So, one more thing I'm going to add to that. If a function passes a horizontal line test, if a function passes the horizontal line test, we say function is 1 to 1, which means, okay, that every number in the domain has one and only one number in the range and vice versa. So now, remember to define a function, okay, and we had that on our test, right? Each number in a domain can only have one range. This says both of those things has to happen in order for it to be 1 to 1. Okay? One element in the domain, one in the range, one in the range, one in the domain. It's got to be that way. And that's what the horizontal line test checks out for you. Okay? We call that 1 to 1. Okay? And you just, if it asks you, hey, how do I know if a function is 1 to 1? Check out the horizontal line test. If it passes it, you're good to go. I'm just looking on these things here. That's one of the first things they ask you about horizontal line testing. Oh, verify functions are inverses of each other. Let me show you how to do that. I want to take one right out of the, I don't know if it's one you got to do or not. Doesn't matter. Oops. Okay. We want to verify F and G. F and G are inverses. How do we do that? Okay. To do that, first of all, you have to know something about the identity inverse, or excuse me, the identity function. Identity function is just f of x equals x, okay? Because if I put 1 in there, I get 1. If I put 2 in there, I get 2. I get 3, I get 3. So what I'm going to do is I'm going to take f of g of x and check to see if it's equal to x. If it is, then they're inverses. If not, then they aren't. So we're going to do function composition. So I'm going to take this thing here, put it in there. Okay, let's see what happens. So I get 3 times 1/3 x minus 4 parentheses plus 4. Let's see what we get. Okay, it's a little weird, but I'm going to take this 3 times that 1/3. What happens to those things? Yeah, I get 1, right? So I'm just going to get x minus 4 left over inside there. Now I'm going to add 4 to that. So what's going to happen to the negative 4 and the 4? What's going to happen to them? 0, so we just get, oh, how about that? We just get x. All right? Now, I should check it the other way just to make sure, because it has to work both ways. So now I'm going to take the f function, put it in g. 1/3 parentheses 3x plus 4. Okay, I'm going to put parentheses around it. Minus 4, like that. Okay? Well, the first thing I notice is I'm going to take 4 and 4. Gives me 0. And notice that gives me x. So yes, they are inverses. Yes, they are. Of each other. Okay? So if you do this, and they don't turn out to be x, it turns out to be something else, then they're not inverses. Okay? But you're doing function composition there. That's how you check to see if they're inverses. And they're going to ask you that. Verify that they're inverses. Okay? It says give any values of x that need to be excluded. So in the domain. So if you had some square roots, you would just have to say, hey, you know, we can't have x to be a negative number. All right? Okay? That's inverses, which is a lot of stuff. But any questions on the inverses things you want? Such a quiet group tonight. I don't know.
It's actually pretty self-explanatory.
So you saying you didn't need me?
No. It helped a lot, absolutely.
That's all right.
No good ways of teaching.
Oh, no, math books are terrible. Yeah, unless you want to get some sleep. Read it. No, they're terrible. I never read one that was very good. All right. Anyway, yeah. So, obviously we have no quizzes. There's nothing to quiz you on. All right, so I'm just going to be honest. So I'll give you some problems to work on. And if you want to come up and see kind of where you are grade-wise, I can show you that. You'll have to have your GO number because that's how I have to do it. All right. But if you're not interested in that, then you can do what you want. I'm not going to talk anymore. There was a good question, but I should say that, though, before I completely not talk anymore. And it was Rhea, right? Rhea. Rhea had a good question here on 279. Okay, number 7, right? Okay, and she said, hey, what the heck's going on with this here? I got to find f of g of 1. How do I figure that out? And it doesn't give me functions, it just gives me this table. All right? Well, so how do I do that? Well, okay, well, here's what I said. Well, first of all, you start with g, right? Because we're going in, that's how that is. It's written like this. I wish they'd write it this way, but they don't. Okay. So we're going to start with the g, and we got to go to 1. So I go on the table, I go to 1 on the table where it says x, and then I go down to g and see what it is. So what does it say g of 1 is, according to that table? 0. Okay, now that becomes my input into the f, right? Because I go to 1, spits out a 0, and now I go to 0. So I go to 0 on the x, okay? And now I go down to the f function and see what it says. So what does it say the f function is at 0? -1. So there's my answer, okay? So f of g of 1 is equal to -1, and that's how you do that. All right, so it's kind of goofy because you got to bounce around a little bit, but that's how it is. You just go inside out, so you start with the g, go to 1, okay, g is 0, okay, now that becomes my input into my f, so I got to go to 0 on the x and figure out what f is at 0. Okay, so that's how you do those. Okay, so that was a great question that she asked. So I want to go over that.